All right, everyone, we are back, and now we're going to look at a very specific example, and let's try to predict some of the behavior and verify the rules. And I think it's always nice to kind of see it in action. So let's look at this system. So we are going to have, there are how many number of poles? So we have basically a pole at -2. We're going to have 2 poles from this, so there are 3 poles in total. There's 1 0, so m equals 1. So n minus m branches, so 2 branches will go to infinity or asymptote. So let's go ahead and let's verify kind of step by step, and let's look at the resulting root locus, and let's kind of verify each of those rules. I think that's a good activity. So, or a good analysis tool. Let's see. Where is that system? Is it? Here it is. So this is our L of S. So these are our poles. Great. And now let's look at, I want to just look at the root locus. Actually, we can look at it right here. So here's our root locus. So we can see already what's happening here, and I'm going to actually shrink it up. So what are we seeing here? So we have, as we see, 1, 2, 3 poles, 1, 0. Good. Are we symmetric about the real axis? Yeah, you can see this pole migrating over here. I like it. To me, I think we're in a good spot. Is that also at -2? Yeah, that makes sense. They're all the real values. Anyways, so are we symmetric? Rule 0, we're not violating it. Fantastic. Let's go through rule 1. So are each of these 3 being, okay, so let's see. We have 3 poles. How many branches? How many colors? Blue, yellow, green. So first one, we're good. M branches will terminate at the finite 0. So n 3 minus, or actually, m branches, meaning m branches, how many m's? So basically we see here, this goes to infinity, this goes to infinity. So this branch, 1, is going to the 1, 0. Perfect. N minus m will go to infinity or post asymptote. So that's 2, 1, 2. Perfect. So rule 0, rule 1 is verified. Rule 2, real axis segment. So a point, so these are all starting at -2, -2, -2. So if I do a vertical line here to the right of -2, we know that there's 0 poles and zeros. If I do a line right here to the right, I have 1, 2, 3 to the right poles. So you see, this whole axis will lie here until I hit this 0, and then it will stop. So it won't basically go past that. So rule 2 is satisfied. Asymptotes, branches going to infinity. Now here's where things get a little bit nasty. Let's calculate this centroid. So our centroid is going to be, actually we can kind of see this here, the sum of the poles, over minus the sum of the zeros, and we can kind of see this here. So these are the sum of the poles, this, and that's the sum, minus the sum of the zeros, divided by n minus m, or 3 minus 1. So here, this is saying that the asymptotes of basically where those poles go off to infinity, they will intersect at -1. And we can actually see here that as we go to infinity, and you can actually see it when it's really exaggerated. So let's say to 100. And let's visualize this a little bit here. You can see that those values, those asymptotes, as it goes to here, the x-axis value is basically that -1. So there you go. That's the asymptote. What about the angle departure? Let's go ahead and go up here. The angle departure is a little, it's always a little bit tricky, but we can get it. I want to kind of keep it here. So the angle departure will be 2k plus 1 over pi. divided by n minus m. So we can look at that departure angle for the different values here. So 2k plus 1, 2k plus 0, how many, and k is basically the angle of each of the departure that goes basically to infinity. So start first with k equals 1, then k equals 2. So you're just going to have 1 times pi over 3 minus 1. So that goes off at 90 degrees, which makes sense, right? So that angle, or the departure angle, will be this, and the departure angle here, basically from this minus 2, basically to here, or so it'll be that minus 90, basically 90 degrees, and then minus 90 degrees. So let's go ahead and bring that back here. Where are we at? So you can look at that departure angle of that, basically as it goes to infinity. So that's kind of the key thing here. So you start off at like basically as you started at infinity, it's like minus 90, and then you kind of bend towards here. So fantastic. So actually, that's the angle of departure. So basically, or that's the asymptote angle. Excuse me. Well, of that intercept. Basically, the angle of the asymptote to the axis. What about the angle of departure and arrival? So that's kind of like the slider bend. This one's a little bit more complicated to calculate, but I've basically written up a little function to help us out here. And it actually, all you have to do is specify basically the angle from the real. You have to specify all of your poles, and then you're going to specify the pole that you're interested basically relative to this kind of minus 4 value here, or actually relative essentially to your x, your y-axis value. So here we can see this is we're interested right now here in this pole, and actually I can kind of let's blow up the angle departure here. So if I look at the angle departure. So the angle of departure, you see what we're specifying, the pole, and then our pole list, and then our 0 list. So our 0 is essentially that value there, so that's going to be our angle of departure. You can look at some of these other functions, but let's go down here. Let's keep moving. Here we go. So we need to specify that 0. So for pole at minus 2, the angle of departure will be what? 180, and that makes sense because it's just moving to the left there. If we look at the angle of departure of our minus 2, and it's measured from the positive real axis. So positive real axis and counterclockwise is basically positive. So if I'm looking at what pole is that? Minus 2, minus 4, so that bottom pole. So clockwise is positive, so this is negative, so it's going down and to the right of minus 63 degrees. And for here, it's going, as we can see from the positive one, it is going up and to the left. So we verified all our rules. Again, somewhat of a tedious exercise, but it's still really important. It's important to kind of see. And sometimes you need really depending on that angle, right? If you're designing a system that it's really tight and you have to kind of be there and it's taking off at it's taking off at a huge angle, that's going to be a problem. So next time we're going to get into basically rule 5, which is one last rule, which is a breakaway break-in point. But this is a good example to look at rules 0 through 4. So we'll see you next time. Thanks. Bye.